Okay, so we're going to go through the MAT question, question 3, which I sent to you last week. And I think this one's really about your powers of integration and generalizing, which is quite a nice gentle introduction to generalizing. They don't ask us to do this in the question, but if I were you, once you got to the middle part, I would check when we've got a generalized result that it works for the answer that we gave in part B. So let's have a little look at our exam paper. And 5 parts, and we've probably got about 25 minutes to get that done. Obviously, if we can do it quicker, all the better. So at first, I'm going to draw the axes and draw these graphs of y equals root of x and y equals half of x. The square root, of course, is known. It goes on up to infinity, but it's concave, isn't it? And goes to the origin, and there's no negative values. Y equals half of x. Well, clearly that's going to go through the origin, isn't it? And we'll have to work out where it intersects, although you can probably guess when you've done your graph. Okay, so I've just marked on the square root of 4 and the square root of 2 because it makes it easy to see that I've got that graph right. And let's just see where these graphs meet, just check. So I've cancelled on x, that's why I know it's going to the origin, because x could equal 0, couldn't it? That's one solution, and of course the other solution is that x equals 4. So let's now draw on my second line, y equals half x, and clearly they want us to work out that area. Right, so let's go on with part 3, and now that I've drawn my graph, I've just got to do the area in between. So clearly, if I find the area underneath the curve and take away the area of the triangle underneath, I should be left with the area between the two lines. Okay, so don't forget that dx, because we're going to be integrating with respect to x. And the area of course, half times the base times the height. Okay, and then let's look at that integral. Well, if we raise half up by 1, so x to the power of 3 over 2, isn't it? And of course, if we divide by 3 over 2, we get 2/3, and we're putting in 4 and 0, and taking away 4. That's the area of the triangle. So if we have to worry about when we evaluate this definite integral, because when we put 0 into the x, it clearly equals nothing, doesn't it? But when we stick in 4, the square root of 4 is obviously 2, 2 to the power of 3 is 8, and 8 times by 2/3 is 16/3. Take off the 4, which we should write as 12/3, and there's your answer, 4/3. Now, as I said at the beginning, we get an opportunity to check our answer. So let's just see what they wanted in part 4 was for us to generalise. So the first thing we're going to do is find out where does the square root of kx meet the line mx. And it looks to me like we know that for sure it's going to go through the origin. So let's not worry about that solution. Let's square both sides. So kx is equal to m squared x squared. And of course, if I can cancel an x on both sides, it means that x, one out of the x's must equal k over m squared. Now, if I've got the x coordinate, I can easily find the y coordinate, because look, one of these lines just says is y equals mx. So if I just multiply my x coordinate by m, then I'm going to be fine. So that's going to be k over m is the y coordinate. Okay, so all we have to do now is integrate between, remember it's with respect to x, we're putting the x coordinates, so k over m squared and 0 of the underneath the curve, which is kx to the power of a half, and of course we're going to take away another triangle, and that's going to be half times by the base, which we know is the x coordinate, and the height, perpendicular height, which is the y coordinate, and that's going to work out quite nicely, in fact. What's that imply? That implies that, actually, I just need to look at the question. So yeah, what you might be wondering, why is there an extra k in the denominator? Remember, we have to use the sort of inverse chain rule, that we've got kx in the brackets. So if we differentiate, just check you get back to where we started from, and you would in this case. Okay, and that's going to be evaluating for this. We're going to see that we're going to get a k cubed over m cubed with a 2/3 with a k in the denominator. Take away k squared over 2m cubed. That's going to tidy up quite nicely. In fact, it's going to go to 2 squared over 3m cubed. Okay, and the same is the same denominator for the triangle. Okay, so let's make them over a common denominator. So she'll choose 6m cubed. Okay, and that's going to be what, 4k squared take away 3k squared, which equals 1k squared. So k squared over 6m cubed would be the area as between the sort of generalised part. Yes, that's a really good idea to check part 2, because we thought the answer was 4/3. That was when our value of k was 1 and our value of m was 1/2. So let's just see if we stick that into the substitute that into the formula, our solution, general solution. We should end up with 4/3. So we're going to get 1 over 6 lots of an eighth, which does tally up to 4/3. So, which is really good. So we definitely got the second part right. We knew that ahead anyway. It looks like we got the generalised part true as correct as well. Right then, the last part, part 5, is said, can you show that the area between these two curves is always, when is it always greater than the value of the x coordinate of the intersection, not the 0 one. Okay. And we know the general coordinate for the x coordinate is k over m squared. So it's just a question of sorting out this inequality. I'm going to multiply both sides by m squared, because I know it's positive, it won't affect, and I'm going to divide both sides by k squared, which is also positive, so I don't have to worry about my inequality sign flipping around. And now if I just tidy this up a little, I get 1 over 6m is going to be greater than 1 over k, and of course if I flip those two fractions now, then of course I do have to think about what happens to my inequality sign. I believe the answer is that k has to be greater than 6m.